Hi there, welcome back to the channel, and in today's video I'll be showing you about how a MOSFET works. Now, what do I mean by MOSFET? It means metal oxide semiconductor field effect transistor. It's kind of a handful to say, that's why we've abbreviated it as MOSFET. And I think you'll see it a bit more clearly if I show you how it looks. So let's draw it. We always start with the substrate, so for an N-channel substrate, for an N-channel MOSFET, we need a lightly doped P-type semiconductor. And for these contacts here, we want heavily doped N-type for the N-channel. So that when it's doped in this way, it's basically, we don't have to work as hard to get the results that we want. If it was doped like just generically, we would have to apply more of a gate voltage to get the same results than if we doped it this way. So that's why we've done it like that. This is the oxide layer. For example, silicon dioxide. Okay, so here's the metal contact as well for the gate. For example, aluminium. So you can see a bit more clearly now how it gets its name. We have metal, we have oxide, we have semiconductor, and it works by means of field effect. So when we apply a voltage at this gate, it doesn't, because this is an insulator, it doesn't go through to here. It doesn't fully conduct into here. Instead, it kind of attracts and repels carriers by means of the electric field, what's known as the field effect. And I guess that's another thing you should know about the MOSFET is how you draw it in the circuit. So you can see here is the gate, the source and the drain. So let's see how it works in enhancement mode. So we'll draw the gate contact like this. And this is for the N-channel enhancement mode. Now, what do I mean by enhancement mode? What I mean is that we have to apply a voltage at the gate terminal to turn on the device so that it can conduct from the drain to the source to drain, so that we form that channel. So I think this is more clear when I show you this plot of the drain current against the gate voltage. As you can see here, we have to apply a minimum amount of voltage for there to be a drain current. And this minimum voltage is what's known as the threshold voltage. That's the minimum voltage we need to turn the device on. But there's another mode as well. So we have also depletion mode. Let me draw a few here. So it's kind of the same thing, with the arrow pointing towards here, towards the substrate. This is the substrate pointing towards the main thing here. But now these are all connected. Like if you see, these are like, I specifically drew it so that these are like, have gaps. These are all connected. Again, we'll draw the same plot, but instead, the threshold voltage is negative. That's the minimum needed to turn on the device. So if you look here, this is 0. But look, at no gate voltage, there is a drain current. So that is a clear indicator that this operates in depletion mode so that it conducts even when there's no gate voltage. This is something you should be aware of if you ever do work with MOSFETs, of course. So now that I've covered that, let's look at the surface conditions. What happens when we apply a gate voltage to the gate terminal? So we'll kind of take like a lateral cut here, and I'll draw this here. And let's start with accumulation. I think that's a good place to start. So we're going to look at a MOS diagram, metal oxide semiconductor energy band diagram. If you're not familiar with energy band diagrams, I suggest that you watch the first video I did on semiconductor theory in my channel, and that will show you the kind of the ground basics of energy band diagrams. But one thing I will remind you of here for band diagrams is that electron volts, positive goes up, negative goes down. But for actual voltage, positive goes down, negative goes up. It's kind of the other way around, if you can see it that way. So let's start with the diagrams now. So this is aluminium, the metal, silicon dioxide, the oxide part, and here's the semiconductor part. For this case, let's work with P-type silicon. So always a safe bet you can do when drawing your MOS diagram is to start with the Fermi level, because that stays constant throughout all of the layers. So now we can start by drawing the valence level, the valence band, sorry, the intrinsic energy level, and the conduction band. So because we apply a negative gate voltage, a negative gate voltage, we accumulate holes here at the surface. Or should I say the interface of the oxide and the semiconductor. So by applying negative gate voltage, the voltage will go up at the gate. So you can make this rule that the gate voltage is less than 0. It can't be positive at all. So with that rule, then that must mean that everything else will bend towards following the gate. So by doing this, at the interface, we've accumulated more holes because the Fermi level is closer to the valence band. And there's a couple more things here. This kind of a difference in the oxide layer here is what's known as the oxide voltage. And the difference in the conduction band here is what's known as the surface potential. Okay, I've covered most of the things here for accumulation. I think it's now good for us to move on to depletion. So by depletion, what that means is that I've depleted the interface of all mobile carriers, so that there are no holes. Well, there are holes in electrons, but it's intrinsic at the interface, so that it can't really conduct. Depletion. Okay, so this time, again, draw the Fermi level, valence level, intrinsic energy level, conduction band. So for depletion, think about it. Think magnets, opposites attract. So to repel positive holes, we need to apply a positive gate voltage. Just like if we want to accumulate holes, we applied a negative gate voltage. Think of it that way. So this time, the gate voltage will go down because it's positive. Oops. So the gate voltage is greater than 0. We can make that rule. But now it will bend the other way. The oxide layer will bend the other way. So that at the interface, look at it, the intrinsic level is equal to the Fermi level. So the Fermi level is not closer to electrons, it's not closer to holes, it's in the middle, so it's intrinsic, okay? So that means there are no mobile carriers at this interface here. That's what I want you to do. This might be quite abstract, quite different to how this would look, but it's just the same thing. It's just tilted, and we've taken a look a bit more in depth of how it works. So we know this, but how would we like to form an N-type channel? How would we do this? So if we apply a negative gate voltage to attract holes, we want to attract electrons to form a channel. Electrons have a negative charge. So therefore, we need to apply a positive voltage, but a greater positive voltage than it was for depletion. We call this inversion. You'll see why. So again, we'll draw the Fermi level, always a safe bet. But this time, the gate voltage will be quite accurately, as we would like, ideally, to be equal to the threshold voltage, like this. This is the case of enhancement. So that now we've applied a great enough positive voltage so that it can start conducting. And as with the rest of these, it will all bend down, following the gate voltage bias. Okay, so here it is for inversion. So we have conduction band bends down, intrinsic bends down, so does the valence band. But look, this is the key thing, the interface. This is where the magic happens. So at the interface, look, the intrinsic level is now gone below the Fermi level at the interface. So what does that mean? Theoretically speaking, there are now more electrons than holes at the interface. We've now started to attract electrons to the surface here. So we've theoretically, again, started to form the channel. But how do we know how much gate voltage to apply? We need to look at the threshold voltage. How would we calculate it? This is how we would calculate it. So we have charge of an electron multiplied by the accepted concentration, multiplied by the depletion width. So this is the depletion width. And this is the oxide capacitance. And this is the potential barrier. So how to get this is equal to roughly 0.026 natural log for the n-channel case is Na divided by Ni. So accepted concentration divided by the intrinsic concentration of your semiconductor. How did I get 0.026? It's an approximated number, but I'm kind of running low on space. I'll write it up here. 0.026 is, well, I should say approximately equal to at room temperature. Okay, so this is Boltzmann constant, this is the temperature in Kelvin, and this is charge of an electron. So units of Boltzmann constant is joules per Kelvin, and if we have the temperature in Kelvin, the Kelvin will cancel out, so then we just have joules per coulomb, and that's what gives you electron volts. And it's quite specific at room temperature. Unless stated otherwise, you would assume this value. How do we get depletion width? That's a good question. So XD is equal to the square root of 2 epsilon 0 epsilon s 2 times barrier potential, charge of an electron. There we go. So this is the permittivity of free space, and this is the specified permittivity of your semiconductor. So this has the units of the permittivity, but this is unitless. So you just multiply this by this to get the equivalent permittivity for your semiconductor. And to get the oxide capacitance, that is equal to the thickness of your oxide underneath the relative permittivity once again, and the permittivity of your oxide. So again, this has the units, this is unitless, this is kind of like this, and this is kind of like a base for your permittivity of free space. And this oxide thickness, you just have to make sure that these have the same units. So if this was in meters, you'd have to convert this into meters. If this was in centimeters, you would have to convert this into centimeters. So I think that covers quite a fair bit for inversion. Now let's look at strong inversion. Okay. Okay, so this time it's not just any regular inversion, this is strong inversion. Okay, so this time it's kind of the same old story again for inversion, but we've just applied it even more positive gate voltage once again. So this is Fermi level, this is intrinsic energy level, this is conduction band, valence band. Again, this is down because it's positive. This time it's greater than the threshold voltage, and we can assume that this threshold voltage is much greater than 0. And of course, this will bend down. Okay, I haven't drawn enough space. Okay, there's one thing I forgot to tell you about the inversion just now. I should have. is that this difference here is the potential barrier. But this time for strong inversion, this is the surface here. This time this is where the surface potential is. In the regular inversion, I just want to make that really clear that this difference is the same as here. So for regular inversion, this was the barrier potential. But let's look at the threshold voltage equation one more time. Okay, this time we have to account for the inversion charge that's accumulated at the interface. Qi is equal to minus COX, the oxide capacitance, this, and multiplied by Vg minus Vt. That's the threshold voltage equation for strong inversion. So now I think I've covered a fair bit of theory about MOSFETs today. So now I'm just going to quiz you a little bit. A couple questions to test your knowledge on how MOSFET works. So I'll just cut to that. Okay, so here I have some questions for you to try. How lucky. So question 1, what surface condition would you choose to form a channel in a p-channel MOSFET, and why? I want you to explain your answer. Just saying your answer is okay, but you need to prove you understand it by explaining your answer correctly. That's why I asked you why. And for question 2, what would the gate voltage polarity be for a p-channel MOSFET and accumulation? Why? Why is that? And what surface condition will you choose in question 3 to break the channel in an n-channel enhancement mode MOSFET? Why? Yeah? That's the big question. Why is this happening? I want you to explain that. So take your time, have a think, and I will explain it in just a second. Okay, so now I'll go through the answers with you guys. So question 1. So what surface condition would we need? What would we choose to form the p-channel? So inversion or strong inversion, that would be the right answer. So that's correct. But why? Why do we need this? So to form a p-channel in the p-channel MOSFET, we need to attract holes from the n-type substrate. I want you to explain that. That's the answer I'm looking for your explanation of why we're using inversion and strong inversion. For question 2, what would the gate voltage polarity be for a p-channel MOSFET and accumulation, and why? So positive voltage. Why? Because in accumulation, we attract the majority carrier of the substrate. So for a p-channel case, we need positive voltage to attract the majority carrier of electrons from the n-type substrate. But if it was like the n-channel MOSFET, it would have a p-type substrate. So that would be a negative voltage, which would attract the majority carriers, which would be holes in the p-type substrate. And for question 3, what surface condition would we need to break the channel? So, accumulation or depletion? Either of those would work, because they both kind of, well, this would be technically more correct, strictly speaking, from the theory, because this totally stops any of the minority carrier from the substrate forming the channel. So that would work. In the case of the n-channel, electrons are repelled kind of in the way there, sorry. So the electrons are repelled by the negative voltage, and in depletion, well, depletion is kind of a grey area, to be honest, but I would accept that as an answer for the time being. So this is all I have for today's video on the MOSFET. If you have any more questions, or if there's anything else you'd like to know about the MOSFET, please let me know in the comments and I'll get back to you as soon as possible. Thank you very much for watching.